Good morning or good afternoon, whatever time you're doing this. Hopefully not in the middle of the night. What we're going to look at in this video is just an introduction into hypothesis testing, especially with binomial distribution for WJEC AS. Start with just a quick exercise because you should be at this point comfortable working out probabilities with binomial and using the notation for it. So have a pause of this video, work through these two questions and this problem. Let's just see how you get on. So pause the video now. Okay, hopefully you've had a go at these. Let's have a look at it. Hugh and Kim play 9 games, so that's our sample size of n. Probability Hugh wins in a game is 0.65, so that's my p, my probability of success. If we count Hugh winning as a success. So hopefully the first thing you did was right. You're showing the examiner here, I know x is distributed binomially. Sample size n, 9, 0.65p. I need them because I'm going to put that into my calculator or into my formula to work out this first one. But I want Hugh to win exactly 4. Now this values either come from using the formula, which is in your formula booklet, or you've used binomial PDF. Okay, so in your calculator, 2 binomials, binomial CDF and PDF. So this one is a PDF as we're looking for an equals to. Now with B, we want that he wins at least 5 games. Okay, so at least 5 meaning 5 or above. Now in order to use the CDF for my calculator, I need to be changing CDF, remember only works out less than or equal to. So in order to work out greater than or equal to 5, I think of the opposite, which is less than or equal to 4, but I need to do 1 minus because I'm considering the opposite. Okay, and that's what we've been working over the last few lessons. Into your calculator, you can use stats tables. The number should come out as 0.1717. 1 minus that, and we get 0.8283 as an answer. Now, if you've still got any problems with that, you need to look over your notes, because most of what we're going to do is working through binomial problems or working out probabilities. Okay, so moving on. So what we're going to do here is sort of set the scene of what we're doing and why we're doing it by just looking at a few scenarios, getting you to think a bit. So if we had a coin, we're going to toss it 30 times and it landed on heads 15 times. Would we say that coin is biased? So, is it giving me more heads than it should, more tails than it should? Is it a fair coin? 30 throws, we'd expect to get 15. We've had it 50% of the time here. So, in a perfect world, that is sort of what we would expect. We'd expect to get 15 heads and 15 tails. So I'm happy to say that the coin is fair, unbiased. What about if I had it 30 times again? Okay, thrown it 30 times, tossing it 30 times. And this time I've had 18 heads. So I've had more heads than I'd expect. It's 60%. But it's going to happen. We're not always going to get this perfect scenario, and rarely we would. 18 is pretty fair, I'd say. So I'm thinking here that we wouldn't say the coin is biased. I'd say it's a fair coin. But what if, let's take it to 50 times, and we've got 36 heads. So percentage-wise, that's 72% of the time. I'd expect to get 25 heads, but I've got 36. Has it just, happened by coincidence? Am I just having bad luck or good luck, whatever way you want to look at it? I'm going to let you decide on that one, whether it's biased or not. Scenario 4. What if this time it was 400 times I tossed it and got 290 heads? Now percentage-wise it's 73%, so it's really similar to scenario 3. But does the fact that it's 400 tosses of a coin change it in any way? We're expecting to get 200 heads out of that 400. I've got 90 more heads than I'd expect. Now what you've learned with GCSE is relative frequency. When I do something more than, the more I do something, I should be getting closer to its true, relative frequency. So I should be getting closer to 50% if it was a fair coin. So, you know, again, I'm not going to say anything about scenario 4 for now. I'm going to let you decide for yourself if that's a biased coin or not. But hopefully you can see the difference between these two. Even though it's the same percentage, the fact that I've done it more, you might be more ready to say scenario 4 that it's a biased coin. Now, this is the whole point of hypothesis testing. We have these scenarios where, you know, I need to answer a question, is it biased or not? And I can do it by looking at the probability of me getting 290 coins or more it will be out of these 400s. If it's a small probability, I say it's biased. If it's a large probability, I'm happy to say it's still a fair coin. And that is the purpose of this hypothesis testing. Putting a value, putting a probability on these type of scenarios. So I'm going to go through these 4, work out probability and just discuss them with you. So hopefully you recognize it as being binomial. You know, we're tossing it 30 times, there's my sample size. Getting aheads. Now, here's the important part. I don't know if it's a half. I have to take sort of a default stance. You know, when we get a coin, we assume that the default normal coin has a probability of a half for heads and half for tails. Okay, so I have to assume that. And that's really important. This half is, I'm going to discuss this quite a bit. So this is my assumption that it is a fair coin. And we've tossed it 30 times and got 15 heads. So you might think, just initially, I'll just work out the probability of getting 15 heads. If you did that using your calculator or formula, you'd get 14%. Now, you know, this is always going to be sort of relatively small. If we do exactly one value, it's always going to be quite small, you know. So what we do instead is we look at an extreme. So instead we look at the fact that what was the probability I got 15 or more. Alright, so I go extreme. It's not just 15, it's 15 or more. Alright, what was the chances of me getting 15 or more heads? Working that out comes out as 57%. So there's a really good chance of me if, and this is the important bit, if it was a fair coin, right, with a half, if it was a fair coin, the chances of me getting 15 heads or more is 57%. Okay, which is quite likely. So I'm happy to say that that is still a fair coin. Okay, it was likely to happen, so it is a fair coin. Okay, because it's a good enough, it's a high enough probability of it happening. And that assumption, I'm assuming it's fair. Because that's a high probability, you know, there was a good chance of me getting it. One thing I forgot to mention in that previous slide was how we worked out this probability. So remember, we're using binomial CDF. I need to get it as less than or equal to. So I would do 1 minus x less than or equal to 14. Right, this is 15 or greater, and I want to do 1 minus the opposite of that, which is 14 or less. And that should come out as that 57% again. So in scenario 2, I've still got n as 30. My p is still 0.5, as I'm still assuming it's a fair coin, which is really important. This time I'm working out the probability again, 18 heads or more. Okay, that's really important as well. So working that out again. On my calculator, I need less than or equal to, so I'm going to go less than or equal to 17, and 1 minus that, because that's the opposite. It comes out as 18%. So let's recap, that's 18% chance of me getting this sample of 18 heads or more if the coin is fair. And that's a pretty high chance, you know, that's 1 in 5 times. So I'm still happy to say that this is a fair coin. Okay, it was likely that this scenario happened if the coin was fair. Let's look at 3. N is 50 this time. P is still a half, still a fair coin. This time I want to calculate the probability of getting 30 heads or more. Okay, now I don't know why this says 36, you know what I'm like. That does say 30. So what you should have done here is x less than or equal to 29. Okay, I'll change that for the handout that I give you, but it does come out as 10%. Okay, so we're getting lower. So let's recap: 10% chance that if the coin is fair, then I got 30 heads when I rolled it, tossed it 50 times. Now we're sort of getting into the, is that a low, is that high? So it's a sort of a grey area. 10% could be considered as low, could be considered as high enough to say that it was fair. I'll let you decide on that one. Scenario 4, N is 400, P is still a half, still a fair coin, was probably going to get 240 heads if the coin is fair. Working that out, you get this, which is 0.004%. So, really low chance. So remember, what that's telling you is a really small chance of you getting this sample of 240 heads if the coin is fair. Now, because that was very unlikely to happen, what we say is that the coin is not fair. Okay, because that was the assumption we made. We assumed it was fair, and there was a small chance of it happening, so therefore we say it was not fair, and therefore the coin is biased. Okay, and that's, you know, that's more dry cut than this scenario 3. You can go either way than that. Now there's this fluffiness about, you know, at which point do I say that it's fair or not, and WJEC give us guidance on this, which will take me to the next slide. So what we've got here, now the p-value that I'm talking about here, this is just the probability we've been calculating, okay, the probability that observed value or more an extreme. Okay, so we're always working out a less than or equal to or a greater than or equal to. That's really important. Now the way WJEC want us to tackle it is if you get a probability of less than 1%, they want you to say that does say percent in some weird way. Yeah, that just got worse as I was going along, didn't it? Now I can't wrap it up. There we go. 1%. There we go. There you go. Right, so they want us to say if it is 1%, if the probability of it happening is 1%, they want us to say there's a very strong evidence for rejecting the HO. Now I'm going to come back to this HO. This was the assumption that we made. Okay, so for us it was that it was a fair coin. Okay, so if it's a small chance, 1% chance, we're going to reject that it was fair. If it's between 1 and 5%, then they want us to say that there was strong evidence. So we're going from very strong to strong evidence of rejecting the HO. HO, fair. It was fair. Okay, I'll explain more about HO in a minute. Now, if the probability was greater than 5%, they want us to say that there was insufficient evidence. So we're not accepting, okay, what we're always referring to the HO, right, whether it's fair or not. So I'm saying here that there's not enough evidence to reject that it's a fair coin. All right, so I'm not accepting that it's a fair coin. I'm just not rejecting that it's a fair coin. A bit like a law of law, you're either guilty or not guilty. You never said that you're innocent. You just insufficient evidence to suggest you're guilty. All right. So, what is this null hypothesis? Well, this null hypothesis is sort of your default stance in a way. And so you can see it's a statement about the parameter. The parameter we're always testing is the probability. Okay, so P. The null hypothesis is assumed true until evidence. The alternative hypothesis is the claim that we're making, and we're trying to find evidence to support this. So if you think of our coin example, we took that default stance that the coin was fair, and the coin that was fair meant the probability was a half. Okay, that's what we assumed. Okay, and P being the probability of getting a heads. Nice writing here. There you go. Now our H1 is our alternative hypothesis. That is what I'm trying to test or trying to look at evidence for. So we were trying to look at whether the coin was biased towards heads. So if it was biased towards heads, I'd be getting more heads than I should, i.e. the probability of getting a heads was greater than a half. Now for these, your HO will always be P is equal to some value. Okay, if it was a dice, we'd assume P is a 1/6 if it has 6 sides. For H1, you'll have 3 versions. If you think it's more likely to happen, it's greater than. If you think it's less likely, you would go with P less than a half. Alright, so if I was saying that heads is less likely, okay, so that is another version. And the last version would be if you're not sure, right? If you're not sure you're getting more heads or not, you would say that P is just not equal to 0.5. Okay, so it's not half, but I don't know whether it's less than or equal to. Now, for future reference, these first two, okay, these two are called one tail. They're called one tail because it's going one way, all right, less than, greater than. Whereas this one, do my arrow, sorry about that, this one is called a two-tailed because it could go one of two ways. It could be a less than, or it could be a greater than. I don't know which way it's going, so I call it two-tailed. They're important for when I work out probabilities later on. Right, so moving on to some other keywords. Okay, so what we did on the previous slide was something that we have to do as a first step in any test that we want to do, and that should always be done before carrying out the data or the experiment, okay, so before collecting data or doing the experiment. So if I'm assuming that a coin is biased, I should state that first and then toss the coins. I wouldn't roll a dice and then assume that I'm getting more 5s. I should have an assumption and a hypothesis before doing an experiment. Step 2 is then carrying out the experiment. And some keywords for you. Test statistic, okay, is a value that you'll get from doing the experiment. So when we were tossing that coin, we would count in the amount of heads, okay? So that X value was the test statistic, and that was the amount of heads. Okay, I'm just going to shorten that to amount of H's. Okay, so the test statistic is what you're collecting data on, something that you calculate or you can count. Once I've got that, I then go to step 3, which would be calculating the p-value, or the probability of me observing that test statistic. Okay, so we were calculating probabilities of X being greater than or equal to some numbers. I think one was 30, wasn't it? Okay, so that's my third step, and that'll then lead me to the next one. So the last step that we've got is making the conclusion, so looking at my data, my probabilities, and seeing what I'm going to do with it. Now I'm afraid there's a lot more key terminology here that you're going to have to learn. It is going to be relevant this year and next year for the A2, so do learn it. It is going to be a head blag to start with, but do keep with it. Now what we've got is this critical value. Now when we were looking at those heads, now imagine I was tossing it 30 times. If I had 16, we would say it's a fair coin. If it was 18, still a fair coin. At which point do we say, right, this is not fair? This is not a fair coin. And this is what the critical value is, a cutoff for when we reject the HO. So in our coin example, maybe we'd have said, if I was tossing it, and let's say it was 30 tosses of a coin, we might have said, right, enough's enough. If I get 20 or more, if X is greater than or equal to 20, all right, then I reject the HO. Then I reject that it's a fair coin. So the critical value is 20. Okay, that is my critical value. That is my cutoff point. Anything after 20, I am saying is not fair. My critical region is that it's all the values of X for which you would reject the null hypothesis. Okay, so you can sort of see it as a little number line. Okay, so these are my X values. I had 30 maximum. Okay, because I was having 30 tosses of a coin. Can go down to 0. So this part, if I land in here, if my observations land in here, then I'm rejecting. So that critical region there, and that's when I'm rejecting. So reject. Okay, So this is the danger area. You go in there and you're rejecting that it's a fair coin. Significance level is the probability of rejecting the HO if HO is actually true. Okay, so that's us saying that it's not a fair coin when it actually is a fair coin. So significance level is the probability of being in that area there. Okay, because that's where I'm rejecting the HO. So it's the probability of being there if the P for our case is 0.5. Okay, so I'd have to work out the probability of being in that region, and we've set it as 20 and calculated from there. I will give you a list of these, explaining them and so on, so don't worry if it doesn't quite get there. We'll go over them numerous times over the next few weeks and the next year as well. Good. Okay, so the final thing we'll do is we'll have a look at an example. If I was you, I would pause this, have a go through the steps that we were discussing, see what you can do, see what's made sense and what's not, and then I'll go through it with you, and hopefully that'll clear things up. Okay, so pause now and have a go. Okay, so let's have a read through. Zach and his D&D 7-sided dice. Okay, so 7-sided is important, and he's suspecting it's biased towards the number 4. Now that's important that he is thinking, he's making a hypothesis before he does the experiment, and then he rolls it 60 times and records the number of times a 4 is rolled. And after rolling it 60 times, he recorded 4 15 times. Okay, so hopefully we notice it as a binomial. We've got n as 60. Okay, 60 throws. Because this is 7-sided, the chances of getting a 4 is 1/7. Now, step 1 of any hypothesis test is saying what the null and alternative hypotheses are. So like I said earlier, HO is your default stance. Okay, we're assuming it's a fair coin. So a fair coin would have a probability of getting a 4 as 1/7. Your alternative, H1, is what Zach believes. Now he believes it's biased towards a 4, and therefore the probability would be greater than 1/7. Okay, which makes it one-tailed. Now step 2 would be collecting the data. We've already done that. He's collected the data and got that the test statistic is 15. Okay, so that's the test statistic. We're then moving on to working out the probability of this happening. So we want to calculate the probability that he got 15 4s or more. So remember, always extreme. To do this, think of the opposite, 1 minus. Opposite of 15 or more is 14 or less. Calculate a time binomial CDF. Hopefully it comes out as nearly 2%. Let's just remind ourselves what this has actually worked out. We've assumed if it's a fair coin, the chances of me getting 15 or more 4s is 2%. Ask yourself, is that a small chance? Yes, it's a small chance. A really small chance of that happening. And the problem is the fact that it was fair. So think of the WJEC guidance though. If it's between 1 and 5%, we're going to say there is strong evidence for rejecting the HO. Okay, so we're rejecting that it's fair. Therefore, the evidence suggests that the dice is biased towards 4. Okay, there's a small chance of this happening if it was a fair coin. Therefore, we're going to say it wasn't a fair coin. And that is our hypothesis testing. And those are the steps I want you to go through every time. Now, in order to practice this, I've got a little task for you to do by next video. Okay, so what I want you to do by next video is I'm going to give you access to some multiple choice quizzes. You're going to select one or more. You're going to answer them honestly. Count how many of the questions that you got correct, and then carry out a hypothesis test. And what we're testing is whether you're better than a monkey or not. So let's say this multiple choice question had 4 options, okay, 4 choices. They range from 2, 3, and 4, I think. Okay, so imagine we had 4 choices. Your null hypothesis would be that you're a monkey. Alright, and if you're a monkey, chances of you getting a question right or randomly picking one is a quarter. We're gonna test whether you're an expert in the whatever the quiz is. I think one's Disney and Premier League and maths and so on. Now, if you're an expert, the chances of you getting one right is going to be more than a quarter because you should know something about each question. I want you to go then through the steps, get the test statistic, calculate the p-value, come up with a conclusion. Okay, and that will be your homework in a way for the next video. Any questions, pop me an email.